All right, thank you very much. My name is Morgan Hendry. I'm the Break the Chain domain lead for the Mars Sample Return campaign, and I'll be talking a bit about how we plan on breaking the chain of contact with Mars. We go to the next slide. The Mars Sample Return campaign is going to be the first endeavor since the Apollo program to deliver material to Earth from a body of potential biological interest. This places us squarely within NASA's Category 5 restricted return classification and leads us to implement a technical response that includes things like accepted, approved sterilization modalities, redundant containment, and modalities to break the chain of contact with Mars. What I hope to convey through the course of this presentation is that the MSR team is recognizing the seriousness of restricted sample return. Starting as early as 5 years ago, we began work building a tool set to break the chain of contact with Mars and bolstered that effort with robust modeling, testing, and system verification techniques. Go to the next slide. So NASA is developing an overall strategic approach for backward planetary protection. This is really a two-front effort. The first will be assessing the risk of Mars material to Earth's biosphere. Lisa Pratt will be discussing this a little bit more in her presentation. What I'll be talking about today is the second prong of this approach, which is responding with robust engineering mitigation. While Lisa and her team will be looking at the risk of Mars material to Earth's biosphere, the campaign will be proceeding forward with a conservative approach, treating this material with caution until it's proven otherwise. We'll be leading this approach through the Campaign System Engineering Management Office, producing a detailed implementation plan that will start to address the roles between NASA and the European Space Agency. And finally, we'll be using the NEPA process with the appropriate stakeholders, potentially including the opportunity for public comment. The next slide. So let's start to talk with a little more detail about what break the chain and containment assurance are. So break the chain and containment assurance are really only two of the elements that contribute to back planetary protection from Mars sample return. The thing that makes them unique is that they need to be locked down sooner in this whole process because they're tied to engineering systems. They're managed through a combination of factors, including conservative engineering design, robust margins, and detailed analysis. Break the chain we define as an active surface-to-surface process to satisfy backward planetary protection goals by prohibiting the uncontrolled transmission and release of Mars material of concern into Earth's biosphere. I'll pick out a couple of things from that definition. First, this process is active. We have to engage with it. It doesn't solve itself. It's surface to surface. So break the chain does not happen at a single event in the flow of Mars sample return. It relies on deliberate steps along the way. Third, it centers around Mars material of concern and can utilize strategic methods to inactivate select Mars material to ensure that we have an overall safe return strategy. In short, break the chain is how we separate Mars material from Earth's biosphere. Once we break the chain of contact, we then have to assure that we remain contained and isolated from the outside environment all the way back into sample containment on the Earth, or into the sample facility on the Earth. This is where we utilize containment assurance. Containment assurance represents engineering steps taken to ensure that Mars material of concern remains isolated from Earth.
Morgan, we're getting a lot of audio. Worse. Previously that go away on it.
Is that any better?
Is audio improving? People are reporting echoes.
I have my computer muted. Not sure what's happening here.
It's not a network, but it's a network. I get congestion. Shoot. Stand by.
Is this any better?
Yeah, that's cleared up now.
Okay. Well, I'm sorry. I just clicked mute my speaker within Adobe Connect. I don't know if that did anything, but we'll proceed. Okay, so where were we? Containment assurance. So containment assurance represents the engineering steps we take to ensure Mars material of concern remains isolated from Earth. So within this approach, we're utilizing things like a robust engineering design, control of the load environments that are applied to our system, and selective redundancy where needed. So containment assurance is how we keep Mars materials separate from Earth's biosphere. Let's move on to talk a bit about the tool set. So we could go to the next slide. So as I said before, break the chain would not be accomplished in a single step. We utilize the effect of sequential operations to reduce the quantity of Mars material that we're carrying through our architecture from one point to another. As we've begun to study this, we have found that there are certain pinch points that offer a tremendous amount of leverage in controlling this material. And I've indicated those down on the bottom of the slide. What we want to try and do is utilize specific engineering functions at each of these pinch points to show that we have a manner to control and close this back planetary protection challenge early in the campaign and give ourselves room to grow as we move through and discover new things. So this is part of our approach to ensure we have a robust margin to ensure this problem stays closed. So over the past 5 years, the team has explored a broad swath of technologies and techniques that we can start to apply to this challenge. And we received some excellent guidance from our sterilization working group, a consortium of academia, industry, and government who have advised us on ways that we can robustly inactivate Mars material. And I'll let Lisa talk a little bit more about our work with them in her presentation. But out of this effort, we've identified 3 major tools that we can use to break the chain of contact with Mars. The first of these is particle transport modeling. This includes things like particle adhesion, transmission, and emission. This is extremely powerful, and as we've moved through our particle transport story, we routinely see order of magnitude knockdowns between sequential steps of Mars sample return. The problem with particle transport modeling is that you can't robustly control it. It can only be relatively controlled. And as the amount of Mars material begins to decrease to smaller and smaller values, you need to rely on more deterministic modes to effectively complete your break the chain operation. This is where containment and sterilization comes in. Containment includes things like sealing, encapsulation, isolation, and blocking. It enables you to robustly wrap Mars material within a protective barrier to prevent its release, or shield off hardware selectively from the Mars environment. Finally, sterilization, when applied strategically, lets us take care of the last bits of Mars material that have escaped encapsulation. So what I'll do over the next 2 slides is start to describe how we've mapped these 3 techniques into Mars sample return, both independently and in conjunction, to start to form an architecture breaking the chain of contact. So we go to the next slide. So what I'm going to do, so I'll say there's a lot of information crammed on these next 2 slides, and let me give them a little bit of an overview to how I'm going to walk through them. Effectively, what I'm going to do is tell this break the chain story twice. I'm going to start at Earth and show manners or methods in which Mars material could get into Earth's biosphere. We're going to try and trace that source of the Mars material back to the surface of Mars and then reverse direction. And as we walk back from the surface of Mars to the surface of Earth, I'll discuss the engineering steps we're taking to break the chain of contact and assure containment. So starting now at Earth, after our return trip from Mars, there are three major players in this break the chain story. The Earth Return Orbiter, which is carrying the remnants of the Capture, Contain, and Return System payload, the Earth Return Module, which in turn is carrying the Earth Entry Vehicle inside of it. Inside the Earth Entry Vehicle, we have two robust redundant containment vessels, which enclose the orbital sample, which in turn has our sample tubes in it. The first vector, which could carry Mars material into Earth's biosphere, is the Earth Return Orbiter. During terminal rendezvous with the orbital sample, there's the potential that material can get on the exterior surface of the Earth Return Orbiter. In the event of a divert failure, the Earth Return Orbiter could carry this material into Earth's biosphere. The second vector comes from spontaneous emission of Mars material from the surface of the orbiter. So this is a phenomenon we've observed in several missions in space. And since the Earth Return Orbiter is already on an Earth return trajectory, that particle could potentially follow that trajectory into Earth's biosphere. The third vector is a somewhat pathological case of the second, where this material lands on the Earth Entry Vehicle and is able to ride the Earth Entry Vehicle back to Earth's surface, potentially hiding in the cool wake. The fourth vector looks a lot like the third vector, except for the source of that contamination. Here in the fourth vector, the EEV is contaminated before it's ejected from the Earth Return Module. Finally, the fifth vector relates to the entry, descent, and landing process. Either the Earth Entry Vehicle has not provided the appropriate environment to the containment vessels to assure their functionality, or the containment vessels have a flaw within them that permits them to open and release Mars material. So as we've looked at these five vectors and looked at their mitigation, we find that it falls into two camps. So you click once. The first is we want to minimize the amount of Mars material that we get onto the Earth Return Orbiter. The less Mars material we have in our system, the easier this problem will be to address. Second, if you click again, we want to enforce a clean zone for all Earth Return hardware. This really opens up the potential for robust containment options and an ease of verification and validation of our break the chain strategy. So now let's walk back to the surface of Mars. You can click again. So as we've studied this, we've come to the conclusion that we are primarily concerned about material with which we bring with us from the surface. As such, the first point in which we start this break the chain process is on the surface of Mars during the loading and processing of the OS for launch. So we can click again. So Austin did a great job of laying out all the elements here, and I want to highlight two of them. The first one is the Mars Ascent Vehicle, which has a MAV payload assembly sitting on the top of it and an orbital sample mounted inside. That system lives within a thermal enclosure on the sample return lander. Additionally, we have the lid of the orbital sample, which lives inside its own enclosure on the sample return lander. By keeping each of these systems isolated from the Mars environment, we can dramatically reduce the amount of Mars material that collects on them through the course of the mission, reducing the exposure time to approximately 3 to 4 sols. Now, if we want to bring these samples back to Earth, we eventually do have to expose them to the Martian environment. So we click again. And as we open the thermal enclosure, you start to let in Mars material, which can adhere to the outside of the MAV, the inside of the MAV payload assembly, the outside of the OS, and the inside of the OS. We can protect large portions of the OS and the MAV payload assembly through temporary barriers installed between the OS and the MPA. As we proceed forward, click again, we'll have to expose the lid of the OS for a short time to the Martian environment during its installation onto the orbital sample. Lastly, we click again, we'll have to remove the barriers from the MAP payload assembly prior to launch, which again opens up that volume to exposure for a short amount of time. We click again. So the aggregate effect of all this is we have tried to minimize the amount of Mars material that we collect on the surface. This amount of material is further reduced during the launch process as aerodynamic stripping and heating inactivates or removes the bulk of the material on the outside of the Mars ascent vehicle, leaving that which is enclosed within the MAP payload assembly and on the OS. Through the ejection process and subsequent deorbit of Martian material, we find that the primary vector of material from the surface of Mars towards the ERO is from the OS itself. Even with this reduced particle load, if you click again, we have to assume that we are creating a dirty environment around the ERO and the capture, contain, and return system. Therefore, we need one final boundary to ensure the cleanliness of Earth return hardware. And for that, we established something called the clean zone. Could you click again? The clean zone is a barrier we build into the capture, contain, and return system that is impervious to Mars material transport. We verify this on Earth, and we maintain it in flight through robust structural margining. The result of which is, if we are flying our mission within our bounds, we can be assured that Mars material will not enter this zone. So now this presents a challenge. We have an OS that may potentially have Mars material on it, that we have to get into this clean zone without the transfer of Mars material. We accomplish this through something we've developed called aseptic transfer. You click one more time and then go to the next slide. So the aseptic transfer process uses a double-walled lid and braze material to seal a primary containment vessel shut, to sterilize its steam line and block the ingress of Mars material from a dirty environment to the clean. If we click once, I can start this video. This process begins when the OS is seated on the double-walled primary lid assembly. This assembly is seated onto the base of the primary containment vessel, and we begin to heat our four-way braze joint. Once we apply heat and the braze melts, three things happen. First, you sterilize any Mars material that may have landed on this seam line. Two, you seal off your entry path, blocking the ingress of Mars material from the dirty environment to the clean. Third, you seal your primary containment vessel shut, blocking the output of Mars material. At the end of the day, when these seals re-solidify, you have successfully brought a OS with external contamination into a clean zone without the transfer of Mars material. So can we click again? So naturally, you may start to ask the question, if we're applying heat next to the OS, are we concerned about sample integrity? And the answer to that is no. So we've done a lot of work over the past couple of years, both in analysis and test, to show that a combination of localized heating and our titanium primary containment vessel shell do wonders to protect the OS from the ingress of heat. We've also started to look at thermal gaps and thermal insulation to block radiative transfer to the OS. So these combinations of factors, by our current assessment, show only a delta T of a couple of degrees C in the sample tubes. And we'll continue to work to make this less as we move forward. But if you click again, after completing this process, we've sealed the OS into a primary containment vessel. We now want to robustly contain that to improve containment assurance. So if we click again, we next install a secondary containment vessel. Now, since we're in a clean zone already, we have relieved the secondary containment vessel of the burden of sterilization during its sealing process. Thus, we can start to use things like compression seals and friction pawl latches that we've derived from MSL, SMAP, and Mars 2020. You'll also notice a set of prickly features up on the secondary containment vessel. Those are motion limiting features which enforce directionality on Earth impact and ensure that a rebound event doesn't send one of the nested containers into the lid of another. This again is all part of containment assurance. If we click again, this contained OS lives within our robust passive Earth entry vehicle. The Earth entry vehicle, as I said, lives inside this clean zone, which doubles as a micrometeoroid and orbital debris garage up until the moment of release. You can click one more time. So between the moment of release and entry at top of atmosphere, we wanted to offer the Earth entry vehicle a little more protection against micrometeoroids and orbital debris. Click again. We've elected to use heat TPS to offer superior micrometeoroid and orbital debris resilience over PICA. You click one more time. After completing the entry and descent process, we arrive at landing, and we have two strategies to lower the amount of loads that our containment vessels see on impact. The first comes from our landing site. The soft soil does an incredible job of attenuating the impact energy and actually delivers us our science load case that I saw folks discussing on the chat window. But we recognize that there may still be off-nominal landing conditions that we run into. So you can click one more time. One of the ones we're looking at specifically is a hard surface landing. In that event, we've added impact attenuation material inside the Earth entry vehicle. And this crushable attenuates the landing environment, provide a more relaxed set of loads for our contained off. So we go click one more time. And then we'll click one more time. There's one additional thing that we can do after landing to ensure we've broken the chain of contact and assured containment. And that is to encase the Earth entry vehicle itself. By doing this, we mitigate the risk of small leaks within the two containment vessels. And through additional things like landing site remediation, we may be able to treat the landing site itself to ensure that any material that may have ejected from the Earth entry vehicle is taken care of. Next slide, please. As I mentioned, we've done a lot of work over the past 5 years in preparation for this, and it's impossible to show it all, but I'll highlight a couple of things. One of the first things I'll show you is some of the test beds we've set up for some of our brazing work. The first one you see on the lower left is a quarter-scale induction brazing system developed by a team here at JPL. We've got a number of those quarter-scale test articles below. And what we've done is, over the past couple of years, we've started moving from these quarter-scale coupons, which we've used to suss out our process, into a full-scale system, which you see in the larger picture on the right. So this is a full-scale induction system with a combination of a seating mechanism and a separation mechanism to try and demonstrate this entire process. Additionally, what you see in that picture is a smaller brazing system, the smaller ring that's resting on top of the white one, which is our next generation brazing prototype using resistive heating. As we've learned things from our sterilization working group, which are shown at the right, we found that we can reduce the temperature required for particle sterilization below 500 degrees C, which starts to open up the ability to use heating techniques that are more in line with the traditional heaters we use in spacecraft. The last piece of technology I'll talk about is this thing on the bottom right. So one of the challenges we faced in looking at our V&V problem is how do you verify particle transport below 1 micron? One thing we've been exploring is the use of fluorescent nanoparticles and quantum dots to do leak checking. And so what you're looking at is an overlay of a SEM image of a gridded plate that's been salted with fluorescent nanoparticles. We then have gone and re-imaged that plate at about 40x magnification, and you can actually see the halo of re-emission from these particles. And so what this presents is a potential means in which we could do V&V at sort of real hardware scale with particles that are smaller than a wavelength of light. If you go to the next slide. So as I move to close here, I'll say again that we're proceeding with the development of a multi-pronged strategic approach for back planetary protection implementation across the campaign. We've taken many of the concepts you've seen in this package through sequential design reviews to select our principal technology elements. And then finally, the architecture as a whole through a review back in December. In January, the MSR campaign adopted it as the baseline. So presently what we're doing is we're transitioning from a technology development team to a flight team. We're staffing up to design some of these key mechanisms, moving towards a brazing demonstration this year at full scale, and looking to integrate our contained OSSEs into the EEV test campaign late next year. So in closing, I'll go back to this point I made at the onset, that the MSR team really recognizes the seriousness of restricted sample return. So throughout this process, people in this team have really stepped up to embrace the complexity of this challenge in disciplines as broad as biology, EDL, metallurgy, law, and mechatronics. And through their hard work and the strong planetary protection leadership of NASA and the European Space Agency, I believe that we can rise to the responsibility that comes with the privilege of being able to bring this material back to Earth for safe study. So, and with that, I think I'll transition to Lisa, who will continue this discussion of backward planetary protection.